Okay, let's start. So this course is about nanofabrication. There are many ways to do the nanolithography. For example, some is based on the light, some is based on the charged particles like electron or ion beam, and other are based on the mechanical process. For example, nanoprint. So first, nanolithography we will talk about is photon-based nanolithography. So here I will talk about how to increase the resolution. So this is called the resolution enhancement technique. So this part is used for the IC manufacturing industry. So now let's look at the basic photolithography. So as you have learned from the NE353 lecture last term, there are three lithography schemes. The first one is called a contact aligner. So in this case, the photoresist is put on top of the photomask. So this way you have the maximum resolution. But the problem is that the mask may be contaminated by the photoresist or maybe damaged by the photoresist. So to relax this problem, so there can be a gap. There can be a gap between the photomask and the resist. So this is called a proximity aligner. But this will reduce the damage to the mask, but the gap will reduce the resolution. As you have learned from the previous course, so the resolution is given by this formula. So for the case of the thin resist film, so the resolution is roughly equal to square root wavelength and the gap. This is the resolution. So third one is the projection lithography. So this is actually used for the manufacturing of the semiconductor chips. So the first two, contact aligner and the proximity aligner, is mainly used for the research, but this one is for the production. But they are also used for the low resolution applications. For example, the fabrication of the LED lamp chip. That is the 10 micrometer feature size. But this one is for the production of the IC chips that has a very high resolution. So in this case, so the photomask and the wafer, they are put on the two opposite sides of this lens. As a result, the photomask will never be contaminated or damaged. So this way, the photomask can be used many times. Another advantage is that because we use the lens, there can be reduction. That means the feature size on the resist can be, for example, 4 times smaller than the feature size on the photomask. This will make the fabrication of the photomask easier because now the photomask has larger feature size than the pattern we want on the resist. So normally when we talk about the resolution, when we talk about lithography, we care about the resolution. But actually there is no limit for the resolution. The resolution here will mean how small we can get. There is no limit. There is no limit for the minimum feature size we can get. For example, here we use a 2.5 micrometer laser beam. So this is a laser beam. So we use this laser beam to expose the photoresist. So as you can imagine, if we expose here to make a structure like this, then we move the wafer a little bit to expose another pattern here, then we do the development process. So by chance, you can get a small feature size. So here the feature size is only 80 nanometer. So that means with this 2.5 micrometer laser beam, we can get 80 nanometer feature size. Another way to get smaller feature size is to control the threshold intensity. If we make the threshold intensity to be, for example, this one, then the resulted feature size will be W. So you can see the W is much smaller than a 2.5 micrometer feature size. So here you see that, so the feature size, you can make it really small, but we cannot make the gratings that has smaller pitch. So what the actual limit is the pitch. So the pitches are limited by the physics, but the minimum feature size are not limited by the physics. Another example, for example, you can have a photoresist structure. You may have this resist structure. So this resist structure looks big, right? Looks big. You can do some process. For instance, you can do oxygen plasma. You can do oxygen plasma to etch the resist. Because of the lateral etch, so in the end, the resist profile may be something like this. Something like this. You can see we can have the resist, really narrow, high resolution resist structures, but we cannot make it denser. So this is the basic point for this slide. So now I can ask you a question. So how? Okay. So now I want to ask you a question. So how small our eyes can see? So think about how small we can see. The answer may be 10 nanometer, so 1 micrometer, so 10 micrometer, or maybe under 100 micrometer, and so on. So which one do you think we can see? So I guess many of you would think 10 micrometer we can see, but actually our eye can see 10 nanometer. If the image, if object is bright enough, if the object is bright enough, we can see 10 nanometer. So there is no limit on how small we can see, but we cannot see how close. If they are really close, if two spots is 10 nanometer apart, obviously we cannot see them. So this is the idea of the difference between the resolution and the pitch. So for the industry, they don't use the word resolution. They use the word half pitch. So if we have the periodic openings, periodic line arrays, so this is the half pitch. So this is like the line width of the pattern. So why it is difficult to get high resolution? So we know that when the light passes through an aperture, through a lens, ideally we got something like this. So we have the black and white. But because of the diffraction, the light profile will be something like this. That means so we have the blurred dose profile. So this blurred dose profile will make the final structure like this. How blurred it is, so as you know from the NE353 lecture, this is determined by a function called MTF. This is called modulation so it's called MTF, which is modulation transfer function. So I think you have learned this from the previous term. So again, so because of the diffraction, the light profile will be something like this. So now let's look at what will happen if we have the light plane wave passing through an aperture with the width of 2W. So you can imagine right after the aperture, the light profile is perfect, a square wave, like a square wave. But after some time, so this one corresponds to the case of the contact printing lithography. So after some distance, which is the case of the proximity lithography, so the light profile become complicated. Those profile is really difficult to calculate. You need to do the integral to have this kind of profile. So this is called a near field of fractional diffraction. So when you get far away, this is the far field from Hopper diffraction. You get the light profile become more predictable. So this one can be calculated, but this one you can only calculate through numerical aperture. So here we can see, so we have the central maximum, we have the minimum, maximum, something like this. So this is another view of the same process. So we have the plane wave, and this is the aperture. We have a square shape, then we have this near field, and we have the far field. So we know that, so for the plane wave, when a plane wave comes to a lens, it will be focused to a spot. So ideally, this spot will be a 0 dimension. That means the spot will be, the size of the spot should be 0 nanometer. But because of diffraction, so what we get on the focal plane is actually something like this. So this one is called Airy pattern. So the radius of the Airy pattern is given by this formula, so 1.22 lambda f over d. So obviously, the smaller the Airy pattern, the smaller the radius, the higher resolution we can get on the image plane. So that means to have higher resolution, we need smaller wavelengths, a bigger length, a smaller focal length. This is called Airy pattern, and this is the case for the plane wave onto the going through a lens. So again, this one say the same idea. So we have the plane wave go through the lens, you get to the area pattern at the focal point. The area pattern at the focal point. So now let's look at how to get the resolution. So there are so this one is determined. This one is proposed by a Rod Rayleigh. So it is called a Rayleigh resolution criteria. Rayleigh resolution criteria. So it is a criteria. It is a criteria. That means it is kind of arbitrary. So some other people may give you different criteria, because Rod Rayleigh he is very famous. So we take this one as the criteria, and also because this criteria is relatively simple to understand. So here we have the two objects. So we have two objects. So after the lens, it forms two images, A prime and B prime. So here what we care about is the image plane. So how close this A prime and B prime can be. So we do not care about the point source. We care about what we can get on the image plane. Which will be the photoresist for the case of optical lithography. So Rayleigh said that we know for the A prime it is this curve, and for the B prime it is this curve. So Rayleigh said that when the minimum of the first A prime overlap with the maximum of the B prime, he said this way we can see that the image is just resolved, can be just resolved. So obviously this is only the property of the lens. It's only the property of the lens. That means the resolution, how close you can put with this lens, how close to spot you can put on the photoresist is given by this R. This R we know it is 1.22 lambda f over d. So it's 1.22 lambda f over d. So here, if this is the area, we have n equal to 1. But if this area has a medium that has the index not equal to 1, so we need to put the f, we need to put the n here. So the d, so the diameter equal to 2 times the radius. So the radius is given by focal length f sin alpha, f tangent alpha. For the small alpha, tangent alpha is similar to sin alpha, so we have 2f sin alpha. So then f will cancel out, we get this number. So we define the n sin alpha. N sin alpha is the numerical aperture. So in n we got 0.61 lambda over NA. So the NA numerical aperture tells the ability of the lens to collect the diffracted light. So the bigger the lens, the more light will be collected. So here I have the comment. Here. So because the image plane will not be at the focal plane. Actually, the image plane will not be at the focal plane. For the lithography with 1/4 reduction, the image plane is 5/4 times f. So this one is not hard to understand. So we know that for our lens, so we have the lens function 1/p plus 1/q equal to 1/f, right? So 1/p plus 1/q equal to 1/f. F is the focal length, p is the distance from the object to the lens. So q is the distance from the lens to the image. So for the case of 1/4 reduction, so q over p equal to 1/4. Equal to 1/4. Equal to 1/4. So from here you can tell q, the value q equal to 5/4 f. So this is the image about the Rayleigh criteria. So when they are well separated, we see it's well resolved. So this one is just resolved. So this corresponds to the Rayleigh criteria. So the sum of the light and the gap is something like this. When they are too close, we got the light intensity profile, something like this. So we can see this one is not resolved. So generally, so here we have the 0.61 lambda over NA. So generally, so we have the K1 lambda over NA. So the 0.61 is replaced by a factor called K1 factor. Now this factor will consider other aspects, because for the relay criteria, only the property of the length is counted. But actually, we know for the lithography, there are many properties. For example, the length, there may be some aberrations. For the resist, how high is the contrast for the resist? Obviously, the higher the contrast, the lower the K1 value. The lower K1 value means higher resolution. So the K1 value also depends on the equipment and process control in the manufacturing process. So again, the K1 value is something really complicated. So anything not related to the lambda, the wavelength, and the property of the length is put into this K1 factor. So from this formula, we know that to have higher resolution, we should reduce the wavelength and the K1 and increase the numerical aperture. But this has some adverse effect, because the depth of focus is given by K2 lambda over NA square. So I believe we got this formula in the 343 course. So you can imagine, so when we have a shorter wavelength or bigger NA, we also get smaller depth of focus. But then the trouble will be, we have small depth of focus, so there may be some feature, some part of the resist may be out of focus, so the image will be blurred. So there is a trade-off between the resolution and the depth of focus. So now let's look at the effect of the numerical aperture. As we have talked about, the numerical aperture is given by n sin alpha. So you can see the bigger numerical aperture means bigger the alpha angle, means bigger length, bigger alpha angle, bigger length. So more light will be collected. So here you can see the image. So the photo mask is the grating, for 1.6 micrometer grating photo mask. So because of the 4 times we know about 4 time reduction. So because of the 4 time reduction, so the feature set on the pitch become 400 nanometers, so 0.4 micrometer on the photoresist. So here we have a big numerical aperture. You get this very high contrast light profile, higher contrast, and also higher image intensity. So we have lower numerical aperture. You get 0.5 numerical aperture. You get this curve. So lower contrast and also lower light intensity. So far we talk about a circular lens. For the circular lens, we have this formula here. We have this number here, so 1.22. So you may wonder, where does this 1.22 come from? So this is because when the light comes in, to calculate the light intensity, at the focal point, we need to know the light from all the spots. So every spot come together to form the light. So that means we need to do integration. We need to do the integration along this circular disk. For the circular disk integration, in the end, we get something. The light intensity here will be something called a Bessel function. So when we do the integration of the circular shape onto the focal plane, we get the Bessel function. So the 0 point for this Bessel function give you this 1.22 number. But this is complicated. But now let's look at what we can do. So here we have a rectangular lens. So this shape is like a slit. It's like a rectangular slit. It's no longer a circular. For a slit, you can imagine after the slit, the light profile, if this is a far field, really far field. But that means the distance from here to here, is many times the opening of the slit. So this far field. So you can imagine the light intensity become something like this. You can also imagine that from here you can see that we have bigger aperture. So we have this curve. It's more the light is more concentrated to the near the axis. So we have small aperture. The light is more spread out. This is why you can imagine If the aperture is infinitely big, you get only the light on the central spot. So here is the effect of the wavelength. So we have shorter wavelengths. We have shorter wavelengths. You get smaller spread. We have bigger wavelengths. You get bigger spread. So for the case of the resolution, as we have seen, we want smaller spread. So here is the same idea. So we know that for the circular lens, this is the front view and this is the side view. So for the circular lens, the light at the focal plane is given by this array pattern. So the radius of the array pattern is given by 1.22 lambda f over d. So here we have the opening here. We have this kind of light profile. We have a rectangular lens that has the length. The length is much bigger than the width. So then we can imagine this one as a slit. So this is the front view and this is the side view. The light intensity will be something like this. You can see something like this. For the case of the circular lens, we know the resolution is given by 1.22 lambda f over d. So then we want to know what is the distance from the first minimum. So the first minimum, the distance here. This one gives the resolution according to the Rayleigh criteria. So we need to know what is this value here. So to calculate this one, so we can do this way. So first, we know we have a lens. So we have the light passing through the lens. We have the light impinging onto the lens. So the effect of the lens will be the same as if there is if this part of the light is blocked. Because anyway, this light, this beam, and this beam, it gets lost. If they get lost, they are not used to form the image. Then it's the same thing as if we block it. If we block it, you can also imagine if we put the aperture. Now, if we put the aperture a little bit before the lens, then the effect, the final effect will also be the same. So this is the aperture. So here is the aperture here. So now we put the lens here. We put the lens here. So this is the case here. So we put the lens right in front of the aperture. So when we have the aperture, the light will be diffracted. So in the total light will be the sum of the different sub-beams. Will be different sub-beams. So the light goes all the directions through this aperture. So now we look at, because we care about a certain spot on the focal plane. For example, this spot corresponds to the beam coming from those parallel light. So all the light come from here. All the light, parallel light, they will be focused to one spot. So what we know, we want to know this phi angle. We want to know this phi angle. So at what phi angle, the light intensity at this spot will be zero. So now let's look at here. So here we have the opening. Here we have this phi angle. Here I draw 3 light, 1, 3 sub-beam, 1, 2, and 3. So we know that if this one equal to lambda, then if this one in the middle, it will be lambda over 2. So that means, so when the light 1, when the sub-beam 1 and sub-beam 2, they have a phase, they have an optical path difference is given by delta L. So this is called optical path difference. The delta L optical path difference is given by A over 2 sin phi. So this one equal to A over 2, half A sin phi. If this one equal to lambda over 2, then we know that sub-beam 1 and sub-beam 2 will cancel out. So this corresponds to the situation of sin phi equal to lambda over A. If 1 and 2 cancel out, you can imagine there is another beam here. So this beam and this beam will also cancel out. So in the end, so all the beam from the top half will cancel out, will be cancelled out by the beam from the bottom half. So this way we know that, the light along this direction, if we talk about the far field, the light along this direction will be cancelled out. So this gives you the minimum. So that means when the phi angle here equal to lambda over A, this spot will be the dark spot. So I hope you can understand this concept. So then we can know the distance from here to here, which is the resolution according to the Rayleigh criteria. So R equal to F tangent phi. For the small angle, tangent phi is approximately sin phi. So then we have sin phi equal to lambda over A. So we have R equal to lambda over A. So this R equal to lambda F over A. Lambda F over A is the same as the 1.22 lambda F over A. That means for the case of the rectangular length, this is 1.0 lambda F over A. This is 1.22 lambda F over A. Then we can do the similar calculation as the case for the circular length. So in the end, we get R equal to 0.5 lambda sin alpha, 0.5 lambda over NA. So that means for the slit, K1 factor equal to 0.5. We know for the circular length, the K1 factor is given by 0.61. So now let's look at the effects of the numerical aperture. So in this case, we can see the mask. The mask is periodic opening, which has this kind of a square function. This is the ideal image on the mask without diffraction. But because of diffraction, the image can be any of this. So we know that for the length, the length give a function. The length is the Fourier transform. The length will do the Fourier transform of the object. Okay, let's continue. So we have the mask. This is the mask. This mask is the periodic openings. So after the mask, the light will be diffracted. So here we have the 0 order, first order, second order. So you can imagine the bigger the length, the more light will be collected. If all the light is collected, the image will be the same. It's also a periodic grating, but it is 4-time reduction. So the image will be, this is the object, image will be something like this. So, but in reality, not all the light will be collected. For instance, if we collect only the 0 order, we get this blanket exposure. So we get uniform exposure. There will be no information of the periodic, grating. So this is the 0 order. So when the m equal to 1, is included, m equal to 1 is something like this. Top. Sorry. This is the sinusoid m equal to 1. If you plus the equal to 0 order and the first order, you get this one. You get this one, right? M equal to 1. If you have m equal to 3, corresponds to this one. M equal to 3 is also collected. You get this curve. So eventually, if you get very, very high order, m equal to 200, you can see the light profile is almost the same as the ideal case without diffraction. So actually, the function of the length is to do some kind of a Fourier series. So any object, if any opening, if this is the square wave, right? So this one corresponds to the square wave. So this square wave can be decomposed into the Fourier series. If you remember what you have learned for your math, you can see. Maybe you can look at this one. So here we have the first order m equal to 1 sin theta term. Second order is 3 theta. Then you have 5 theta, 7 theta. So the more light can be collected, the more light can be collected, the closer it is to a square wave. If you collect only one first order, you get sinusoidal wave. Then higher order, you get this square wave. You can also see maybe this one, the same idea. You can see first order, if you collect second order, become maybe the green color and the other colors. If you look at this one, So this is the zero order, the blanket exposure. This is the sinusoidal wave. If you plot them together, you get something like this. So now we come back. So the higher order, the bigger the angle. From that's why we know that we have theta, 3 theta, 5 theta. So the higher the order, the bigger the angle. The bigger the angle, the more difficult to be collected by the light. So that means how many light can be collected give you how sharp is the image. How sharp is the image. That how sharp means how is the edge of the opening is defined on the image plane. So now let's look at the wavelength. So obviously, the shorter the wavelength, the shorter the wavelength, the bigger, the shorter the wavelength, the higher the resolution. So historically, the industry first used the 433 nanometer wavelength. This is used to make the minimum feature size 7 to 1 micrometer. Then it goes to 365 nanometer. This is the I line. Those two are the mercury arc lamps, G line and I line. This one is used to make the IC chips with 1 micrometer to 350 nanometer feature size. Then go to the Photon fluoride. This is the excimer laser. So this one is used for only 2 generations, 355 nanometer and 180 nanometer. So this 2 generations. So after that, it shifted quickly to 193 nanometer, which is the case for the argon fluoride excimer laser. This one is used to make the chip 180 nanometer down to 32 nanometer. So we know that today is no longer 32 nanometer. Today it is 5 nanometer. So even 5 nanometer, or even a 5 nanometer node, even 5 nanometer node can be made by using 193 nanometer wavelength. So this is the topic of what we will cover in this slide. It's called resolution enhancement technique. By using the resolution enhancement technique, we can get really small feature size using a not so small wavelength. If we want to go further, we go to the EUV lithography, which is 13.5 nanometer. So today, this one and this one, they are both utilized for the lithography, for the manufacturing of the IC chips. So they can both, this one, they can both make 5 nanometer. They are used to make 5 nanometer feature size. So now let's look at, get back to the numerical aperture again. So we know the numerical aperture is given by n sin alpha, n sin theta. So for the case of the exposure in air, n equals to 1. So the limit is 1. So the upper theoretical limit is 1. So in practice, the limit is somewhere about 0.93. This corresponds to the case of 68 degrees. So theta equal to 68 degrees. For this one, we already need very, very big lens. It's 500 kilograms. So actually, as you know, for the camera, a lens is not like a simple lens. It's like a stack of many lenses. We have many lenses. For example, you got one lens like this. You got another lens, maybe like this. Another one like this. You got all the lenses together. So in the end, effectively they are one lens. But because you can modify each surface, you get smaller aberration. of the lens. So it's the same thing for the lithography. There are actually many lenses to get a smaller aberration. We have so many lenses, it can be really big, 500 kilograms. So the diameter of the lens for the manufacturing, that means for the lens here, the size of A here, I guess several tens of centimeters. This several tens of centimeters of the lens, or maybe 1 meter of the lens. So why we cannot get bigger? So one problem is the lens will be too big. Another problem, for the larger numerical aperture, we have the polarization issue. That means the light polarized perpendicular direction and horizontal direction, they will diffract differently. The transmission through the lens will be different when they are near something called the Brewster's angle. So for when we have this numerical aperture, the K1 value we know for the relay criteria is 0.61. So for the single exposure, the K1 value can be can be brought down to 0.25, so times the wavelength divided by 0.93 give you 52 nanometer. You can see that it is still not so small. To make it even smaller, we can further reduce the K1 value by double patterning and triple patterning, as we will see later on in the slide. So again, today, the lithography, so we can use 193 nanometer lithography, immersion lithography, to make 7 nanometer devices, 7 nanometer node. For the case of the combination of 193 nanometer and EUV wavelength, it is used to make the 5 nanometer node. 5 nanometer node we use both. 7 nanometer we use 193 nanometer wavelength. But actually, so here the node is no longer a physical value. It's a more marketing value. 7 nanometer node, the word is called node. The 7 nanometer node does not mean the pitch equal to 14 nanometer. So ideally, we know that the node should be the half pitch. But actually, for today, because marketing, they want to make the number looks better. So 7 nanometer node is no longer 14 nanometer pitch. The pitch is, I think the pitch is about 30 nanometer. Okay, thank you.